Okay, so I'm Ramsay Taylor from the University of Sheffield, but I'm working on the Prowess project. You've probably seen quite a few of my colleagues around, and they've been presenting things. The Prowess project is a great big European project studying testing for Erlang. So I've got colleagues doing test generation, I've got colleagues doing novel testing strategies, I've got various people doing different ways of testing, and I've then ended up being the one that has to check on everyone else. It's a kind of who watches the watchers situation. So that's where test adequacy is going to come in. So what does test adequacy mean? So you're all Erlang developers, and you will have nice bits of Erlang code, I assume. And hopefully you're all writing tests. I've only had one conversation so far with someone that said, oh yeah, I should probably write some tests. Yeah, you really probably should write some tests. So I'm assuming you've all got your Erlang, and I'm assuming you've all written some nice tests for it. And I'm going to suggest that you've got a problem that perhaps you don't think is a huge problem. And that's the huge problem, that you've written your tests, and you run your tests, and they all pass. Now, I think most normal, sane people, they write a load of tests and they run the tests and the tests pass and they feel very happy. You know, my code must work, it's great. I'm done, I can go to the pub, it's excellent. Well, I'm the guy that unfortunately is employed to sit there, and when all of your tests pass, I get worried. I think, well, if you've written all these tests and you've run all of these tests and they all pass and there was nothing wrong, well then obviously you didn't do the right tests, did you? Because clearly I can write 20 tests that will run 20 things, but they'll all pass, and that won't prove anything at all. So the real question, of course, is, having written all your tests, have you actually tested anything? What have you actually tested? And this, of course, can be exacerbated when you get into the test generation. You can spend lots of time, and you can write a beautiful QuickCheck model, and it can be a perfect QuickCheck model. And then you run QuickCheck, and it generates 1,000 tests, and those tests all passed. And you generate 2,000 tests, and those tests all passed. And you generate 3,000 tests, and those tests all passed. Well, do you stop there? Or would the 3,001st test have been the one that found the really critical bug? Okay, so you do 4,000 tests, and then would the 4,001st test be the test that ran the really critical bug? So you've kind of got almost two problems. One problem is, you know, do I need to do more testing? And the other problem, especially if you're not having to write the test, you're generating the test, is, well, okay, when do I stop? I mean, I can run QuickCheck for 3 years, and it doesn't find anything. Does that mean it wouldn't have found anything on the next day? So what we want from a test adequacy metric, and I'm going to suggest to you a few of those in the next 30 minutes, but ultimately what we're asking for when we're asking about test adequacy is, firstly, have we actually tested all of the code? We've built this big Erlang system, we want to actually test it. The very first question is, are there bits of it that we're just not even trying? Because that would clearly not be enough testing. The second bit is, have we tested it in meaningful ways? I'm going to show you some examples in a minute where you can test all of your code, but you haven't actually found the bug. You've tried it, but you haven't tried it in the useful way, or in the way that's going to stimulate something to go horribly wrong later. And then, of course, if we answer no to any of these, it's also quite useful if a test adequacy metric doesn't just say, no, you need to do more. It actually says, okay, you need to do this bit more. Because otherwise you just end up kind of flailing around. Well, I'll try this, so it doesn't make it happy. Oh, I'll try that, it doesn't make it happy. You can run QuickCheck for another 3 hours, and it still doesn't make it happy. It's really nice if the test adequacy metrics can give us a bit of useful feedback. So what I'm going to talk to you today is, I'm going to start by talking to you about code coverage, because that's usually the easiest one to sell people. So cover is already built into OTP, and if you're just running rebuy, you probably are running cover in the background. You just may or may not bother to read the output from it. So code coverage is at least a start for test adequacy metrics, although I'm going to mostly tell you why cover is actually not a very useful test adequacy metric, and we can use some much better ones. But code coverage as a test adequacy metric certainly can help you with that first question of, have you actually bothered to test everything? And that's useful. And I'm going to show you some more advanced code coverage metrics that will help you test it in meaningful ways. And all of that's kind of, here's my block of code, am I really exercising it? But then there are some complementary techniques. So I'm going to talk briefly about mutation testing. If code coverage is saying, have you exercised the code that you've written? Mutation testing starts asking, well, what about the code I could have written instead, or I might have written? Not to mention, am I going to try testing my code in a way that I would just never think of by looking at it? And the third and final point on that one is often the most useful one. You can do code coverage, you can exercise all of your code, and your code all runs and it doesn't crash and it all executes and it gives an answer. But have you actually bothered to check whether the answer's right? Because that's a fairly critical limit on testing. If you've run 1,000 tests but you haven't bothered to check whether any of the answers are right, then you're definitely not doing it. And finally, I'm going to mention model inference. I've got literally one slide on that just because it needs to be dropped in. Model inference is a completely sort of novel way of looking at test adequacy, so I sort of want to mention it to get you to think about it, because I think it might be useful. Okay, so I think we're going to start with some code coverage. Okay, I've got the dumbest Erlang program in the world, and I appreciate that this is the Erlang User Conference, and that you're all elite Erlang programmers, and you can all look at this, and first of all, you can all see exactly what's wrong with it, and secondly, you can all say that none of you would ever write code like this. I needed something that would fit on a slide and would prove the point. So if you can sort of suspend disbelief about this particular Erlang program, what I want you to try and imagine is some sort of 1,000 and 1,500 line Erlang module, and some crazy guy was writing at 2 in the morning, and then he comes into work and he gets hit by a bus, and then another guy has to take over maintaining it, so he changes it a bit, and he tweaks it a bit, and he adds a few bits, but then he gets fired because he was drunk, and now this third person is taking over, and now so you've got this thing, and it's there, and it works, and you need to test it, and you need to maintain it, but try to pretend you can't just glance at it and know what it does. So some of the code coverage metrics I'm going to talk about in a minute, their adoption was actually really pushed by a NASA study where NASA looked at their own code, and I think some of it was their mission critical code. And they found things where various people had worked on. And if we take this long line here and we call that a decision, because you decide whether you're going to do this bit or not, if that's a decision and then the subparts of it, the A equals 0, the B is greater than 4, if we call those conditions, this NASA study found bits of their mission critical code where they had one decision that had over 20 conditions in it, all sort of nested and composed and conjoined, and there may be a couple of professors of formal logic in the audience that could have read them and understood it, but normal people just had no idea how this thing was going to evaluate. So ignore the fact this is small and try and imagine that this is big and complicated and you can't just glance at it. So we're going to test this program. And to start with, I'm going to show you cover. I mean, again, I don't know how many people have even seen the red and black output you can get from cover. 2, 3, okay. Reasonable number of people actually look at it. Some people just run rebar and it says 50%, and that's all. Cover will at least give you this much coverage, but I want to show you why this is really not actually enough. So we want to test this. This is just a function called dv that takes 2 arguments a and b, and it might divide b by a, or it might not on certain circumstances. So let's run it. So we call dv with 0 and 5, and that executes the first 2 lines. And this is my first criticism of cover, of course. Imagine if this wasn't just B. Imagine if there was 50 lines in this top block and only 1 in the bottom. Okay, your code coverage is just hit 98% or something, because you did one half of it, and that was most of the lines. So counting on lines is a silly way of counting anyway. But nonetheless, we've done one test, and we've tried 2/3 of the program as far as cover is concerned. So we do another test, 5, 5. Okay, so A is not equal to 0, so we're immediately going to execute the other bit. So that's great. We've tried the whole program. And okay, it's a small program, so it should probably be a small test set. But as far as code cover as a code coverage metric is concerned, those 2 tests give you 100% coverage. You're finished. Hopefully, everyone in the audience can see that there's a really big problem with this. If we call this with 0 and 2, okay, so A is equal to 0, but B is not greater than 4, so that AND is false, so then we're going to do the bottom block, and then you get a divide by 0, and that's really bad. But you can imagine a circumstance where one guy has written a condition, and another guy has come along later and go, oh, I don't really want it to work when it's big in this, so he tacks on a condition, and a third guy tacks on a condition, and quickly the kind of route through this becomes decidedly non-trivial. So although code coverage with cover told us that we were finished, we definitely aren't finished. So we certainly want something more than cover. So there's various points in between cover and this. Cover is literally just doing what's called line coverage. Have you covered this line or not? From there, I talked about decision. You can do decision coverage, so you have to take every branch and not take every branch. You can do condition coverage, where each of the conditions is true or false. But eventually, the thing recommended by this NASA study was modified condition decision coverage, which is hard to say, but is quite good. So rather than just, cover works by just inserting instrumentation into code to see which line gets executed. So rather than just saying this was called or it wasn't, we're going to at least keep track of how it was called, and we're going to do some evaluation on, well, you haven't just evaluated this, in what circumstances you've evaluated this. Okay, but rather than, as I say, if in our previous program, instead of just having 1 line, it had 30 lines sequential, if you execute the first one, you also execute the other 29. So we don't necessarily care about these blocks of code. What we're interested in is the decision points. We're interested in, okay, do I take this and not take this in various different tests? And thirdly, as I say, you can do decision coverage where for every decision point you take it and don't take it in different tests. But what we really want in MCDC is to not just take it and not take it, but look at all of the ways of taking it and not taking it. So we had an AND, so you can make an AND true by making both sides true. But you can make it false by making the right side true, false. You make it false by making the left side false. You make it false by making both of them false. There's various ways through that. And as we saw with this example, if you cherry pick just one way of getting through it, you can then get the rest of the code to work, even though a different choice of getting through it might make the rest of the code fail. So what we want to look at, we can't look at every possible value for A and B. So we need to sort of have some classes of them. We need to look at, what's interesting combinations of values in A and B. So we look at what the programmer thought were interesting. If he's chosen to switch on these particular conditions, then let's try interactions between those conditions. I've put reasonable in brackets because it's not the complete cross product of trues and falses. There are some cases that are clearly impossible. As I say, with an AND, there's only one way of making it true. It's not interesting to look at different values that make it true. And conversely, there's lots of ways of making it false, but some of them are impossible, as we'll see later. So we don't need the complete cross product, but we need to look at all the reasonable ways of taking or not taking each branch. So here's some output of a much better tool that I wrote called Smother that's going to give us a bit more than that. I think I might show you it live just because it looks a bit cooler. So although this is showing us, where are we? Although this is showing us we can add another test, and now we've got both decision and condition coverage. So if we include this one, we've tried both the conditions true and both the conditions false. We've tried the decision true and we tried the decision false. But we haven't actually achieved MCDC coverage. And indeed, you can see, although I've made 3 tests here, we haven't found the bug. So what we can get from Smother is slightly more information. Rather than just showing that we have and haven't tried things, what we can do with this is then, let's do the last test. So Smother has a compatible-ish interface to cover. So we Smother compile something, then we run our tests, and then we analyze it to file. There we go, it's gone green. But now we can actually look at the decision and talk about not only have we made it false and haven't we made it false, which is shown at the top, but also the meaningful ways of making it false. Like I say, there's no meaningful ways of making it true other than everything being true. But when we make it false, there's actually a sort of matrix of possibilities. We can have one side true and the other side false, one side false, the other side true, etc. So what we're seeing here is hopefully exactly what the problem was, that although we've made this decision false, we've never made this decision false whilst A equals 0 was true. And of course, you can see that that's exactly where the bug comes. So there is a path to that second branch where it does the division in which A is equal to 0, but we've never tried that one. So that's quite fun. This then gives you a much richer notion for your code coverage than just cover. And so internally, this thing is stored as a tree of possibilities. For the decision, it's got a tree of true and false, and then for the conditions, true and false. So if you ask it for a coverage percentage, rather than being a kind of arbitrary count of lines, it's a count of the leaves of that tree that you have or haven't hit. So it should be a more representative sample. But OK, I've just talked for 8 minutes or something about coverage on this decision point, but it's an if statement. But of course, you lot are all functional programmers. So you don't really make decisions with if statements and Boolean conditions and ands. You make decisions with pattern matching. That's how half your decision making is done. But actually, we can apply the same idea that we applied to that to pattern matching. So pattern matching, although it's not a Boolean expression, you have the same criteria as you go through your patterns. Either your pattern matches, or it doesn't match, and we decide whether we're going to do the next block based on the pattern being matched or the pattern not being matched. So what Smother will ask for, I mean, this is the same problem sort of rephrased as function headers. I mean, it's now explicitly 0 and 5, but the idea is the same. What Smother will ask for, essentially, is all the meaningful ways of making a pattern true and false. And of course, usually there's only one meaningful way of making a pattern true, as in to match a pattern. But there may be several ways of failing to match a pattern. You can match most of it and then get this last bit wrong, or you can match most of it and get the first bit wrong. And so we can look, in the same way that we look for the conditions in a Boolean decision, we can look for the components of a complex pattern and make sure that you're actually exploring the different ways of failing that. I'd be interested to know people's experiences, how often this comes up, but I do this sort of thing all the time. I'll have a series of expressions, and I'll put something into the program, and it seems to hit the wrong one. I mean, it hits too early, or it skips one, and I can never figure out why. It's because I put a comma in the wrong place, or I've got too many things on a tuple, or not enough things on a tuple, or a tuple that's got 7 nested lists, and so I missed the fact that it was a quad and not a triple. and so on and so forth. So we can extend this notion of MCDC, this notion of modified condition decision coverage, to apply to pattern matching, which then makes it applicable to all sorts of bits of Erlang. Because you haven't just got function headers, I mean, you've also got case statements, and this is a particularly Byzantine example because I've had to force it to be a tuple and then match on the pair and so on and so forth. But you can see that you've got the same kind of expression is going down through all of it. And so you want slightly more richness from your test. You don't just want to say, I've hit each of the patterns, which is what you get from line coverage. And indeed, if you put too many things on one line, then cover won't even detect that. It'll just detect you hit this line once. So this is giving us a richer notion of coverage. So that's it applied to a case statement, but we can also extend this even to lists and so on. So lists are a more complicated structure. You don't just have a list with the two elements and maybe the first one matches and it doesn't, but you can also fail to match that in a range of other ways. And this is often the point at which some Erlang programmers get upset with me, because I start saying, well, you haven't tried it with an empty list and you haven't tried it with something that's not a list, and maybe you should explore those possibilities. Oh, yeah, but it's supposed to fail, that's the idea. And so we were having a bit of a debate about whether some of these things should be included or not, and I'd be interested to hear people's opinions, but having come from sort of safety critical systems, my attitude is you've exported this function, someone might call it with something that's not a list, you should test that. But I guess maybe you want that one to fail, but maybe it's worth always trying things with an empty list. And it's certainly worth looking at, if you've got a pattern that's got an explicit number of elements in a list, then having a different number of elements so you fall through to the next one, as opposed to having the right number of elements but they're the wrong values. And these are different things that are worth exploring. And of course, this can also expand to some of the communications patterns. So a receive statement ultimately is still just doing pattern matching and Boolean expressions depending on how you choose to do it. So even your sort of message passing between processes, you can actually measure that you're covering. You're sending a representative sample of messages to a process because you've actually explored the patterns in the receive statement. So, okay, so I've said all that about code coverage, and code coverage has its place and it's very good, and it's usually the very cheap option that everyone wants to do. But I mean, the first limitation, of course, of code coverage is that you've written this block of code, and you've exercised all of this block of code. But all that we're really talking about is the code that you have written, not the code that you should have written. You've written this thing, and it's a particularly bad problem if the programmer is also writing the tests, because it's quite common that you misunderstand the problem, and you write an entire program, and then you write a load of tests that are based on the same misunderstanding of the problem, and they all pass on your code. So even having explored your code in all the possible ways, we're still not answering the fundamental question of, is this thing actually working? We just know that it's not crashing. So at the end of having achieved code coverage, although you've definitely exercised everything you've written, all you've said is that I can run all of it without it crashing. So what we might like instead is an alternative. So this is where mutation testing comes in as a complementary technique. Mutation testing, I gather it's really popular in Ruby. I haven't tried it in Ruby, and I'm keen to try it in Elixir, but I haven't tried it in Elixir. But mutation testing, all the stuff I've read about has been in things like C, where you mutate your C and then you see if it still works. Or rather, you see if it notices that it doesn't still work. But so mutation testing, the premise is that we're going to take our program, we're going to deliberately break it in some way. We're going to insert something nonsensical, or we're going to change something, or we're going to break something, and we're going to see if your tests even notice. So this is back to our original question of, are you actually looking at what's happening? You can execute a bit of code and it doesn't crash. That doesn't mean it did the right thing. And as long as I'm fairly subtle about how I change your program, if I change your program and your test doesn't notice, that's probably bad. Yeah, we can have a little bit of a debate about it, but the very early mutation testing tools would just change characters, and of course 98% of the time it didn't compile, and of the other 2%, half the time it was a comment or something. So we're doing something a lot richer. I've got a mutation testing framework for Erlang as well that I'll introduce in a minute. That actually mutates the abstract syntax tree, changes it on a sort of semantic level and writes it back again. So it's definitely changing something real with the code. So it's definitely going to do some different behavior. And if it can do some different behavior and your tests don't stop passing, then are you really exploring what it's doing? So we're going to try and simulate common faults. At least that's what they say. I mean, you can't try every possible change to the syntax tree because that would just be ridiculous. So you try and simulate common faults either with the system. So if you've got a particular domain I don't know, I mean, people working in sort of financial services maybe want to tweak all the numbers and see if anyone notices, see if they notice if I steal, you know, 0.1 of a kroner off the end of everything. Your tests maybe want to be really focused on numbers. Other people that are doing a lot of networking, you might want to deliberately insert kind of latency or deliberately insert kind of lost packets or something. And again, see if your tests are actually exploring that. But the other thing they often want to do is common faults with the programmer. A lot of mutation testing tools are based on common typos, common mistakes, common sort of idiosyncrasies. If you know programmers often type these things wrong, or they often get patterns in the wrong order or something, well, let's insert a few of those and see if the tests notice. Because if I can insert one over here and the tests don't notice, then maybe the real one that I did by accident over there hasn't been noticed either. So there's kind of two sources for mutants. So this is the gist of the sort of process of a mutation testing workflow. You have your sort of Erlang source file up on the top, and you have some set of relevant mutation operators. And the first thing we're going to do is identify the points where we can do it. If I just randomly applied mutants, I'd end up with the same mutant 6 times, and I'd end up with other problems. So first we're going to look at all the places we could apply them. And then we're going to apply n of these random mutations, and we're going to spit out n mutants. So we're going to get n copies of your program, each of which has been changed in just one way. And we're going to see if your tests notice. I've done it deliberately like that. Some people like to have multiple mutants in one file, and that's interesting, but I quite like to... It comes back to the last point on one of my early slides. You don't just want your test adequacy to tell you your tests aren't working. You want to tell it why it's not working. So by having separate files with one mutation, if there's one of those where the tests don't notice, well, at least we know exactly which bit it is it didn't notice. So that's what we're going to do. For each of those mutants, we're going to run your tests, and we're going to get the test results for that mutant. And if it fails, that's good. And this is where the whole language gets very confusing, because you're all used to my test passing, it's great, and I'm used to your test fails, that's great. So at this point, if you run your tests on one of the mutants and your tests fail, that's actually a good sign. That means your tests are working because they've noticed I've broken something. And in mutation testing, that's called killing the mutant. I'm not sure why it's quite so bloodthirsty, but they talk about killing mutants. And the alternative is if the tests pass, that's bad. You know, if your tests still pass even though I broke it, that's called a mutant that's still alive and will try and eat your brains or something. So tests that pass on mutants are generally bad, although we can then have a huge, long debate about what's called semantic equivalence. So it's possible for me to change your program in a way that does change your program but doesn't actually change the meaning of your program. And by mutating the abstract syntax tree, this is a lot less common than it can be if you do things syntactically. If you mutate syntax, you just change the name of something, well, who cares? If you actually change some of the semantics of it, then usually it's different. The problem sometimes is you get if I reorder messages, but actually the requirements don't require them to be in order. Well, it's definitely a semantic difference, but it's not a difference that your boss cares about. So you can have a bit of a debate like that. Again, it's sort of up to you. I had this sort of safety critical systems background where actually the debate itself was valuable. If you take this mutant that doesn't get killed and you take your original code and you say, well, okay, I can see it's changed. I can see the test doesn't kill it. But we all agree that that one doesn't matter. But then you bother to write up 2 paragraphs explaining why that one doesn't matter. I consider that actually a valuable exercise. Usually you learn a lot more about your system by going through that exercise, rather than just sort of throwing the message at any order. If we've explicitly sat down and said, you know what, order doesn't matter, and we've documented that can be valuable feedback in itself. I suspect a lot of you aren't agreeing with me, but whatever. So semantic equivalence is a smidgen of a problem with mutation testing, but often that's a kind of question for you. And it's also a question for how you choose your operators. So although I've made this mutation testing framework, it comes with a few operators, but I'm not necessarily suggesting you take it and you run the small number of operators I've suggested. The actually useful approach for mutation testing, as I say, is to have domain-specific operators. If you're really worried about a specific class of problems, you should have some mutation operators that will simulate that particular class of problems. So what I tried to do with this framework was actually build a thing that would allow you to express mutation operators in a fairly rich way, so you can come up with some interesting mutation operators that are relevant to you. So for that purpose, we use the, the Wrangler refactoring library, which I think maybe quite a few people have seen, and quite a lot of people have seen it as a sort of Emacs plugin, so you can do refactoring manually. It's actually got a kind of programmatic API in the back, and you can use it through Erlang, and you can give it these various patterns, which I'll show you a couple of in a minute. But that allows us to have mutation operators that aren't just tweaking the abstract syntax tree. They can often do some really quite subtle things. And I'll show you some trivial examples, but you can do pretty much anything you want. You can write an entire Erlang program inside one of your operators to change things if you really like. So this is the very simplest possible operator that you can supply. This just changes a plus symbol to a minus symbol, which is not very thrilling. But as I said, we've got 3 parts to this. The first part is the name, which is actually quite important, because when you get your mutant, it's going to say at the top what operator did it apply. So this one's called plus to minus. The second bit, as I say, the first thing it does is tries to identify the points at which it can be used. So this is a wrangler pattern, this x at plus y at. They're kind of meta variables that can just stand for variables. So we're looking for anything that matches this wrangler pattern. And then we've got an exchange macro at the bottom here that's just going to swap the operator in between. So that's the simplest form of mutant, is one that looks for a pattern and then it replaces it with a new pattern. But you've got meta variables, so you can do some sort of subtle shifting around of things should you so desire. But you can do slightly more subtle things as well. You can actually have, as I say, an entire Erlang program sitting in here. So this one sort of swaps the order of cases in an if statement. And yeah, half the time the compiler warns you about this, but it's still interesting to try it. So this is going to match an if statement with a load of guards and a load of bodies. So 1 at is a meta variable, 3 ats is a list of meta variables, and I can't remember what 2 ats is, it's something special. But so having matched an if statement with a list of guards and a list of bodies, we're then going to pick a random number up to the length, and we're going to pick another random number. And we can build a new meta variable called new guards by swapping some of the guards, and a new meta variable called new body by swapping some of the bodies. And we can rebuild the new abstract syntax tree by using our new meta variables. And this then gives us a mutated program. But again, I'd be interested in people's feedback. This is quite a succinct way of expressing something that's actually quite a complicated change to the abstract syntax tree. And I'm hoping you should be able to write some interesting, very domain-specific mutations based on this. And you can do vastly more complicated. This is where it gets hard to fit on a slide. But this one is actually modifying the timeout on a receive statement. So having a receive statement with a series of patterns and a series of guards, and then after, for some bizarre reason, after then comes through with a list of patterns. But you can then modify all of those to be 1/100th of the length. And like I say, that may have some really interesting impact if you've got something that's very sort of time dependent, but you're not waiting long enough suddenly. Are you actually testing that, or are you just assuming that it never happens? I don't know. So we've had code coverage, and that's very good in a sort of positive way of making sure you're exploring all of your code. And then, so as I said, mutation testing is kind of the complement of that. There are, however, some limits to mutation testing. You do have to compile all of the mutants. I mean, there's kind of 2 limitations, and depending on who you talk to, different people object to different ones of these. But the upshot is, like, if you've created 100 mutants, you're going to have to compile 100 mutants, and then you're going to have to run your whole test set on 100 mutants. Now, personally, I've never found the compilation to be a problem. I find if I've got a 5-minute test suite and have to run it 100 times, that's 500 minutes, and that's quite annoying. But you can do them independently, and you can do them sort of a batch thing. Conversely, for some bizarre reason, QuickCheck have a case study where running the test takes them a few milliseconds, but compiling it takes ages. I don't know if it's got a lot of parse transforms or something bizarre in it. So they always object to having to compile lots of mutants. But whichever way around, you should bear in mind that although mutation testing is a nice complement to code coverage is very cheap to implement. It just sort of inserts a few cast messages. You can run Smother, and you can run your tests, and it should have, unless you're doing the crazy high-frequency trading the guy a minute ago was doing, the cast messages can have a trivial cost to you. So you should almost always do that if you're bothering to test your system. You should always measure the code coverage. Mutation testing is more something I see fitting in once in a while. When you think you've finished code covering, okay, now we can do some mutation testing. Because it can be quite expensive. It can take quite a long time to run. However, you can often use the results of that to inform what you were doing before. As I say, if you're running QuickCheck to do generate tests or some other test generation framework, it's nice to have a sort of ballpark of how many tests is enough. I've found situations where QuickCheck will just run 500 tests because that's a nice round number. Now 500 tests maybe only kills half the mutants. 2,000 tests kills 90% of the mutants. 3,000 tests kills 98% of the mutants, and then the last 2% are semantically equivalent. Okay, well, so I don't have to do mutation testing again to know that next time I do testing, I should probably do 3,000 tests. I've now got a sort of ballpark figure on how much random testing is enough. And as I say, given the rest of the Prowess project is quite keen to give you lots of random testing and lots of automatic test generation tools, one really good outcome from this section was to give you some sort of ballpark for enough random testing, because otherwise, yeah, as I say, you can run QuickCheck for 3 weeks, and you know if another day would have done it. So I think that's mutation testing. I want to measure model inference partly because it's a little academic fetish of mine, but partly because I don't think it gets enough press. Model inference is then a completely different way of looking at that. So code coverage, I criticized it because you're very much taking the code you've written and exploring it. And then mutation testing, we said, well, we're going to take the code you've written and we're going to change it and think about the code you might have written. But we're still all fixated on code at this point. All of that is like, well, I've got some code, I might change my code, what's going on? What actually can be quite valuable is to stop and step back and talk literally about what was I supposed to be writing? Or what was I supposed to be achieving? And so that's where model inference can come in. So model inference started long time ago with what's called grammar inference. You look at a series of sentences in a language and you try and build a representation for the grammar of the language. But then a lot of people have taken to applying it for kind of black box learning of systems. If you have a series of traces of a system, things that can happen in a system, or indeed negative traces, things that can't happen, things that break the system, you can look at those traces and there's various algorithms to build up an inferred state machine model of the black box system. So you can kind of say, well, I've always seen it do this, and after it does that, it always seems to do that. You can start to create this either finite state machine or extended finite state machine model of what's going on in the system. However, we can actually apply that as a test adequacy metric. Because if you take your tests and you treat them as traces, I mean, a test ultimately is, I'm going to do this, expect this, I'm going to do this, expect this, I'm going to do this, expect. It's a sequence of things you expect to happen in your program. If we take your test set as a series of traces, and then we infer a state machine, what we've got essentially is a state machine representation of what your tests think they're testing. We've built up the machine that the tests are exploring. And then, of course, you've got the question of, well, okay, we've got this model of our machine. Is that what we thought we were testing or not? So if you've got a QuickCheck model, QuickCheck models are actually semantically extended finite state machines. So you can often compare the two. And it's quite easy to see that if you wrote this QuickCheck state machine that had 5 states, and then you infer a model from your tests, where you've only got 3 states in it, well, why haven't we explored the other bit? And as I say, you can have explored all of the code because this is what was written. And you can have explored all the variations on the code because you're very thorough at exploring the code. But if you just didn't bother to implement that thing that you were supposed to implement that you forgot about, that'll never show up with a code-based test adequacy metric. So a model-based test adequacy metric can be quite valuable as well. So I kind of want to throw that out there, not least because Kirill and I are doing some research on it, and it's always nice to have people interested. So with that in mind, I've got a few conclusions. You really should be testing, but if you're testing, you really should be testing your tests. And let's not start testing the test adequacy tests, because that could get very silly, unless I come back next year and do test adequacy. But, you know, if hopefully most of you have been sold on the idea that if you're writing Erlang, you should be testing it. So I want to sell you on the idea that if you're writing tests, you should be testing them, or evaluating them in some way, which doesn't seem unreasonable, like I say, as long as you don't take the stack too far and waste all your time discussing it. Code coverage is cheap. You know, you can practically for free do this, as long as you're not doing something that's hyper time intense. Code coverage is you really should just always run it. But if you're going to do code coverage, please can you do it properly, because hopefully after seeing my trivial demonstration, if anyone goes, hey man, I got 100% line coverage, you'll understand how little that actually means. You know, I've successfully run every line in my program. It's not a very strong claim. So code coverage is cheap, but please do it properly. Mutation testing, though, is a useful complement to that. As I say, it can be expensive, and you will get a lot of whinging when you kind of have to compile it 500 times and execute it 500 times. But it is worth doing as a complement to that. Again, hopefully I've introduced you to the idea that code coverage may be cheap and it may be interesting, but you need some complementary things. And finally, model inference is very cool. I think you should at least have heard the words model inference once at an Erlang conference so that people have heard of it, and then Kirill and I can sell it later. So prototypes, I've called this prototypes, not implementations. I'm the very first one to admit that I'm an academic, not a really talented Erlang programmer. So if you go on GitHub, you can get Smother, which is an MCDC analysis tool for Erlang. You can get Mu2, which is a mutation testing framework for Erlang. And then StateChum on SourceForge is Kirill's thing that does model inference if you want to have a play with that. We've got various Erlang-y-based things that hopefully still work. Do they still work? Yeah, there's various things for getting traces of your Erlang programs and pulling them in and trying to learn models of them. It even does some automatic learning. So if you give it a module that's got standard OTP like gen server callbacks, it will start throwing some values at those, and then it will learn a bit of model, and then based on that, it will start throwing some new values, and it will learn a bigger model, and based on that model, it will throw some more values and build a bigger model until it sort of stabilizes. So you can just give it a module and tell it to go. It's not brilliant yet, but we're working on new versions. So as I say, those are there. By all means use them. By all means don't expect them to be industrial quality, because I'm not industrial quality, but they do exist, and I'd be very keen to hear if anyone has anything to say. I've been told I've got 10 minutes, but I'm ready for questions. So as long as the question isn't, please can I run my code and tests in your tool right now, live on a projector in front of a lot of people, because, yeah. Any questions? You go first. It was supposed to have the same interface as cover, although I got an email from the OTP guy saying, oh, you don't implement this obscure function. But technically, you start by Smother compiling instead of cover compiling your file. And then you can run some tests. So I've just run the same test 3 times, and then we analyze the file. And when we do that, it spits out an HTML file. And yeah, you're not allowed to ask, but it does have a bit of JavaScript in it. So it essentially is colorized. So in fact, I can show you the more compelling demonstration. If we compile it and don't bother to run any tests, it's all red. If we then run one test, so green means you've explored everything that I can meaningfully expect you to. So a function header that takes 2 arguments that are both variables, you've either never hit it or you've hit it. There's no meaningful decomposition, because if you use the wrong number of variables, it's not that function anymore, it's the other version of the function. And if they're both variables, I can't meaningfully decompose that. So you notice it's got not applicable in a lot of places. I'll tell you right now, this is one weakness of this, is there's certain combinations that are impossible, but it's really hard to prove that they're impossible to that. So sometimes you can probably never reach 100% smother coverage on most realistic things. So you have to kind of figure out what the upper bound is. But for other things, if you've explored it, it's green. If you've not explored it, it's red. But if you've partially explored it, it's yellow. And if you put your mouse over a thing, you get more details about the thing. But then, of course, you can go down the tree. So if you only care about this bit, we can put our mouse over this bit and just get. So again, that's a true or false. You know, we need condition coverage because we've never tried it with a equals 0. But there's no subcomponents to that. Whereas if we mouse over the thing at the top that's got subcomponents, we also see this kind of matrix. As I say, this starts to get filled in with not applicables if there's some combinations that are impossible, but it's hard to think of an example. Does that answer most of your question? It has a couple of other exported functions that will give you numbers. I think you can get percentage or something. Yeah, so you can get percentage, and you can get the internal tree. I mean, so if you want to use the tree of coverage in some meaningful way, you can get this tree of what you haven't covered. But and you do it by module name. Oh, okay. Apparently, you don't do it by module name. This is why I don't do stuff live. Okay, you used to do it by module name. I'll probably change something, but yeah, you can get a few numbers out of it. You had a question. Okay, good. Just don't look at the code and you might still have that attitude. Yeah. Yeah. If you had a guard, partially. Yeah, no. So it doesn't really do the proper path analysis because again, that's actually quite hard. I'm sure some of you elite people would do it, but again, working in computer science department, of course, you get all the professors telling you technically it's undecidable in this bizarre case, which is a nonsense excuse not to do it, but it is a good enough excuse for me to not try to do it. Yeah. Yeah, you could sort of insert some types somewhere. I haven't done it, is the short answer. It would be interesting to do. I haven't done it. It's moderately clever within the scope of one thing. So I think it's clever enough to know that if you've got to this point, it can't be that one. but it doesn't work sort of beyond the scope of one thing it's dealing with. But good question, thank you. The back? So it inserts cast messages into your thing that then cast to a separate process. So one thing QuickCheck found is they ran these really quick tests, and they would run the test really quickly, and then they'd have to wait 5 minutes while the analysis thread caught up. So there's a separate server process that receives the cast message and then does the analysis, and that's a bit of code that really, really could be optimized. And I'd really love to do in Elixir, because it's really horrible to do with this abstract syntax tree and then try to work out which bit evaluates to true and which bit doesn't evaluate to true. But I could quote or unquote it and it'd be wonderful. But yeah, so the analysis process runs as a separate process, and you do have to kind of wait for that to catch up. But it shouldn't slow down what you're doing, is the theory. Yeah, so I mean, QuickCheck are QuickCheck are project partners, so they've, I don't know if they've talked about it a lot, they have what they call feature-based testing. So the trivial version of feature-based testing is to generate a test and then see what it covers, generate a new test and see what that covers, generate a new test, and to keep going until your new tests don't cover anything new. And we have extended it to use Smother instead, so it'll now generate a test that covers a new leaf of the possibilities, generate a test that covers a new leaf of the possibilities, and again, it's still random testing. So unfortunately, it's not intelligently using the feedback, it's just generating a new one and seeing what it covers. But you can use it that way and sort of generate a test set that covers as much of the Smother tree as it can. Anyone else? Oh, yeah, go on. It was not my goal, but then the guy from the OTP packaging team came up to me and said, we don't want to support cover anymore, can we use yours? But could you just add all these 6 features to make it compatible? And I said, I don't want to do that. I'm an academic, I'm not paid to do that. But genuinely, there's that tension that, of course, my project will come to an end in 3 months. And as the previous speaker said, yes, somewhere. I think there's a bug. So it's all on GitHub, so you're more than welcome to look through the bug reports. I think the guy filed a bug report for. There's a couple. It's something to do with the way you stash your results, and then you create some new ones. But you can go back to the stash point. I haven't implemented that. It wouldn't be that hard, but I haven't implemented it. And it's kind of there's things like that where people do actually depend on it, and I haven't implemented it because it wasn't obvious. But anyone else? Go on.
So I'm supposed to run just Smother, right? I don't need to run Cobra.
Yeah, no. But yeah.
And if one in the middle fails,
Yeah.
and it's on an external library, and my test just goes through the line that failed, I'll never test the line below it.
But isn't that true? As in, but that would show up here. So if there were no more decision points, then hypothetically you might not see that. Although I kind of assume you would see the exception. If you were deliberately making it test an exception, and yeah, strictly speaking, yes, but.
Because the decision point would be in another library that you have not injected the cases. So you wouldn't.
I possibly naively assumed that if you called the thing, then you would use the return value for something that would include some decisions, and you would see that they would be read. It's possible that the very last bit of your program calls a function that crashes and is supposed to do 2 more sequential things, but that sounds like a Byzantine. It's not an invalid suggestion, but it sounds like a sort of Byzantine case that, yeah, I didn't explicitly consider, but I think you'd be stretching it to say that cover's really useful because it will find that. Yeah. But yeah.
Okay. Thank you.